Now that we have learned how to work around with conditionals and loops in x86 assembly, let's move on to the last video of this crash course on x86 assembly language. In this video, we learn how to implement switch statements, which requires a little bit more complex logic. Because we already know a lot about control flow related stuff, we are going to directly start off with an example. Okay. So here is our example. We have a switch statement, switch X. Now what does that actually mean? Well, that means that depending on the value of X, we have to jump to the desired computational block of code. What we are saying here is that there would be a bunch of options, but depending on the value of X, I am going to execute only one different piece of code depending on X, one different piece of code. For example, if X happens to be 1, you want to execute this piece of code here. And then we have the break statement. So it is only going to execute one block of code and exit out of the switch statement. But there might be cases called fall through cases that do not have a break statement. For example, if X happens to be 2, this piece of code is going to be executed. However, since it does not have a break statement, it will continue to execute the next switched cases until it sees the next break statement. Okay. And also, if you have any missing cases, for example, we don't have case 4 here. So the default case or the default block of code will be executed if X turns out to be 4. Then we might have multiple labels mapped to the same block of code. So to summarize the switch statement, we might have multiple case labels that are mapped to one block of code. Then we have fall through cases here, case 2 that extends through to case 3 because it does not have break statement of its own. And we also have some missing cases. In our example, the case 4 is missing. Okay, so all these situations needs to be managed and implemented, right? So we have lots and lots of stuff to manage. So how do we implement this high level construct in assembly? Though this could be implemented using the branch structures that we have seen earlier in one of our videos, however, things could get really complicated. So another simpler way is to use jump table to map all these scenarios to a block of code in memory that performs computations corresponding to a particular X value. We will shortly see what do we mean by mapping. So the simplest way is to use the direct jump table. We use a jump table, and a jump table works as follows. So this is our example of a switch statement. And we are going to have a table that has roughly as many entries as the number of keys in our switch statement. So each one of these entries in the table actually points to the address, the starting address of a code block that has to be executed depending on the case value. For example, if our X happens to be value 1, so first we are going to look at the jump table, get the corresponding address, and that's the code we are going to execute. Okay, this is how we can visualize the implementation of switch structure that is nothing more than how we implement if else construct, which is just an alternative to the switch statement. So the target address of the EIP register is changed to the value represented by the jump table, indexed by the case value. It means we are going to look up our jump table, which is just an array of instruction addresses that are indexed with X, which gives us the target location for jump. This is another graphical representation of the jump table structures implemented in memory. So we have this switch statement that has 6 cases, and this is our memory. Here we have the region that has as many entries as the number of cases. These entries are basically the first address of the code block that is executed. This is how the jump table is implemented in memory. The color indicates each block of code in the memory representing different cases of the switch statement. And our jump table is going to map these corresponding cases to the regions in memory that implements a block of code corresponding to a particular case. Okay, so we have case 1 highlighted as green, and it is pointing towards the green block of code in memory. That is, if the x in the case statement happens to be 1. Okay, then we have a fall through case. Case 2, since this block of code does not have a break statement of its own, in which case code block for case 3 will also be executed until it reaches the break statement of case 3. And then we have case 5 and 6 that gets mapped to the same region in memory. There is also a very interesting case, that is the default case. As we said earlier, it gets executed if none of the value of x have occurred. For example, if x is 0 or 4, we are going to jump to the default case. Okay, we can use a jump table as long as the value is lower than 6. And for any other value that's greater than 6, we are going to execute the default code. So the table implementation is just a list of addresses, right? That points to the first location of a particular block of code. And here is how we get it set up in the assembly code. You can see the different declarations in the assembly code. There is a section declared for the data, and you have to also tell the assembler about the 4-byte alignment thing. And since the x86 32-bit architecture is 4 bytes, we have long entries to represent the labels that maps to the address of different code blocks. For example, if we take .L56, that is where the code block for case 1 is implemented. Similarly, for case 2 and 3, we have label .L57 and .L58. And remember that case 2 is a fall through case because it doesn't have its own break statement. We also have the default code block, and all the missing cases are also mapped onto the same label. Then we have cases that do not have any code block of its own, like case 5, which gets mapped to the code block of the next case, that is case 6. So case 5 and 6 gets mapped to one label, .L60. Now let's see how does the compiler implements this table in assembly using an example. This is our switch statement here and its corresponding assembly implementation. Then we have this jump table on the right hand that is declared by the compiler. Let us examine how this code works step by step. So after loading all the parameters from the stack into the selected registers, that is, X is loaded into EDX and Z is loaded into ECX. We then compare the value 6 with EDX that contains the value of X. And why compare with 6? Because the maximum case value is 6 in our example. And recall that the compare instruction sets certain condition codes in the program status word that are used to implement control related logic. The compare instruction is used in a pair with a variety of jump instructions to implement different control flow logic. Here we use the direct jump, that is a jump above instruction that jumps to the default case labeled .L61 in case the value is above 6, that is greater than 6. And otherwise, depending on the value of X, we are going to find the corresponding entry in the table. And how are we going to do that? We use the direct jump using the jump instruction, which says that instead of jumping to a specific address, it jumps to an address contained in an address. And what does that mean? It means that we jump to this label .L62, which is the base address of our jump table. Now the value of EDX gets multiplied by 4 because a long word is 4 bytes and is added to this base address. For example, if the value of X is 4, we have 1, 2, 3, 4, and that's the starting address of the code block for case 4. So we are going to jump to this address and execute the block of code corresponding to case 4. Okay. And if the value of x is greater than 6, it jumps straight to default, right? And this is just to summarize what we said in the last slide. This is how we implement the structure of the table. Each target requires a 4-byte entry with the base address at .L62. We had various addressing modes to access different entries of the table using direct and indirect jump instructions, right? Now that we have defined the table structure, let's see how the code blocks are implemented. So here, suppose that we are interested in case 2 that happens to be mapped to label .L57. It means that this is how the assembly code is implemented. We have a division instruction in this expression, and since this is a fall through case, it is going to continue to execute through the next case block here until the break statement of case 3 that uses a jump to .L63 that implements the exit. Note here that the default case labeled as .L61 jumps to the exit label .L63 to leave or return from the switch statement after executing its corresponding code block. The important thing to notice for the rest of our code blocks in our switch statement example is that you have returns after every single block of code that has breaks, and for case 5 and 6 they are both mapped to .L60 because of missing code block of case 5. Because of missing code block in case 5. The compiler might choose to pull the return statement into each relevant case rather than jumping out of it. As opposed to what we saw earlier, in this version of implementation, the compiler opts to place the return logic inside each relevant case. Okay. And similarly, as previously, case 5 and 6 have been merged into one block of code. This time, the implementation places the return logic inside the block. This is the disassembled code of the switch statement. You can see in this implementation that the compiler has chosen to pull the return statements into each relevant case, right? Missing cases are mapped to default case. Case 5 and 6 are mapped to the same location in memory. So we know all this, right? Now let me ask you a question. Would you implement this one with a jump table? Well, probably not, because then you would have to implement a large number of jump table entries for just 4 cases. Okay, so jump tables are more efficient when you have few case values and you can build a small table for it. The above switch statement can be efficiently implemented with branch statement. Okay, so that is it for this crash course on assembly language. Congratulations, hip hip hooray! You have successfully completed the crash course on x86 assembly language, and now at least you won't have any headache if you come across an assembly implementation. And I really hope that these videos were helpful in fading off some of your fears about the assembly language to some extent at least. And I also hope that you have familiarized with the notions and symbols that were nightmare before taking these lectures. Tech Instance has more for you at store, so I encourage you all to subscribe this channel and don't forget to hit the bell icon to receive important notifications. And if you have any questions, feel free to comment in the comment section below. Thank you.